Okay, so we continue our course of the lectures, and this is the third part of the lectures. Yes. So please, from the beginning, the next one will be the next week, just in 1 week before Easter vacation, and it will be the last one on the next week, on 1 week. Okay, please.
Thank you. Okay, today we are going to discuss geodesic orbit Riemannian manifolds or Riemannian spaces, if you want. This is very important class of Riemannian manifolds because it has some very well-known subclasses such as symmetric spaces, weakly symmetric spaces, natural reductive, and normal homogeneous Riemannian manifolds. Well, okay. A Riemannian homogeneous space, G mod H, with a Riemannian tensor G, is called a space with homogeneous geodesics, or simply geodesic orbit space, or shortly GO space, if any geodesic is an orbit of a one-parameter subgroup of the group G. Hence, if we have some another realization of the space with another isometry group, then we have another property. This is Riemannian homogeneous space. If we drop the importance of the group of isometry, say we consider the maximal isometry group, then we can say about Riemannian homogeneous manifold. It's almost the same, but we should distinguish different homogeneous spaces that realized one and the same manifold. If we discuss Riemannian geodesic orbit Riemannian spaces, but for manifolds, we always suppose that the group G is maximal full isometry group. Okay, good. This terminology was introduced by Kowalski van Hecke many years ago. They initiated a systematic study of such spaces. Of course, such example, such property was known many years before this page of Kowalski van Hecke. And moreover, the first non-naturally reductive geodesic orbit manifold had been constructed by Orlando Kaplan a little earlier. But in this systematic approach, Kowalski van Hecke classified all small dimensional geodesic orbit spaces of dimension less or equal to 6. And therefore, they started very popular direction in differential geometry, not only for Riemannian spaces. There are some generalization for Finsler spaces, semi-Riemannian spaces, and so on, so on, so on. Okay.
Can I ask once again, what is the difference? I didn't get completely between the homogeneous space and homogeneous manifold.
Oh, if we speak about manifold, we suppose that we consider full isometry group as a group G, all isometries. But if we restrict our attention to some subgroup, we can consider some another construction. We can realize the manifold as another homogeneous space with another isometry group. Hence, we have different realization and therefore different problems to classify G invariant geodesic orbit metrics.
Of course, since it is different groups.
Yeah, because it could be different groups. Okay. Now, the main technical tool for studying for such spaces is the following result of Kowalski, von Hacke, and Souris, some additional source by Souris. A homogeneous Riemannian manifold with reductive decomposition is geospaces if and only if for any x and from the P, this is a reductive complement to isotropy subalgebra H, there is Z from isotropy subalgebra such that we have this equality. You see, this is a bracket between x plus z and y, P component of this bracket, and next we consider the inner product of this vector with x. And this should be 0 for all y from P, from all y from P. Z is some vectors from isotropy subalgebra. If it is simply 0 and is 0 for any x, we have naturally reductive matrix, simply naturally reductive matrix, very easy. But this is a little more complicated situation when we can, how to say, correct this vector x by adding some vectors from isotropy subalgebra to have this equality. A little more freedom, to find such z. It should not be 0 in general. Okay. If in addition M is compact, then this condition equivalent to the following one for the metric endomorphism A. Metric endomorphism, it is an operator which could be used to explain what is the difference between this inner product and the standard inner product. This is a property. For any x from P, there is z from H, the same, such that we have this inclusion, x plus z, brackets with A of x is in H. Okay, it's more or less clear. Clear what? It's not so, it's easy to check for a given matrix because we should take any vectors, for example, some basis and some decomposition with respect to basis and so on and so on and so on. We have some not so complicated system of algebraic equation, in fact, not so difficult, not so complicated.
Yura, endomorphism A of what space? P or the whole algebra?
P. Because okay. Yes, we change the metric on
yes,
P.
On P. We only have metric on P. We do not have metric yes. on H. Okay.
Yes. Okay. It's only illustration of that fact that this property is more or less easy to fill, easy to check for, say, small low dimensional example, for example. Okay. Now, some obvious corollaries. This proposition shows that this property to be geodesic orbit space depends only on the reductive decomposition and the Euclidean metric on P. In other words, if we have a geodesic orbit space, then any locally isomorphic homogeneous Riemannian manifold is also geospace because we have the same property, the same equality for these spaces. A direct product of Riemannian manifold is a manifold with homogeneous geodesics if and only if each factor in a manifold is a manifold with homogeneous geodesics. It's also very easy to see. And this is what I said. If we have Z0 for any x, we have exactly naturally reductive spaces. And also, it should be noted that all weakly symmetrics are geodesic orbits, or all weakly symmetric spaces are geodesic orbits. It's not so easy to explain. It's it's quite deep result, really. Okay. Now some structure, a little more structure result for geodesic orbit spaces. This is some notation. The symbols R of G and N of G denote the radical, the largest connected solval Norbil subgroup of G, and the largest connected nilpotent normal subgroup of the Lie group G. It's quite usual notation. And for the corresponding Lie algebra, we have similar notation N of G and R of G for nil radical and radical of G respectively. Okay, let's consider one such result, structure result. It's not necessary to read all of this. We see that there are some restriction for geodesic orbit space, which are on the level of Killing form, on the level of nil radical, and so on and so on and so on. If we consider in details this property, the first, the second, and the third, we see that not all homogeneous space could be geodesic orbits for any given invariant matrix, because there are some restriction of algebraic style. For example, this one, the Killing form B is negatively definite on any H invariant complement Q to nil radical in radical. This result does not depend on choice of methods. It's pure algebraic result. Therefore, we can, if we have some Lie algebra G which has not this property, then we could not construct geodesic orbit space with such G. It's very serious restriction of algebraic type. Okay, I skip all this. And the more simple results, simple to say and simple to explain, let's recall the structure of nil radical of G for geodesic orbit space. This result for by Carolan-Gordon. If G mod H and G be a geodesic orbit space, then the nil radical of the Lie algebra G is a commutative or two-step nilpotent. It's very serious restriction, very serious result. This nil radical should be commutative or two-step nilpotent. No another variant, no three-step nilpotency, no four-step nilpotency, only this one. Hence, we have serious restriction, the algebraic restriction. Okay, and some other structure result by Carolan-Gordon. If we have a general geodesic orbit Riemannian space and KB connected closed subgroup of G normalized by H, then the orbits, such orbits of K through the same points, is totally geodesic submanifold of M. Hence, a geodesic orbit Riemannian manifold. We know this property. I'll explain it a little in more detail later. In particular, the orbits of the radical, an orbit of the nil radical, and of Levy group S that are stable under H to this point, the initial point, are geodesics orbit Riemannian manifolds. Hence, if we have some general geodesic orbit Riemannian space, then it generates some other naturally related to the initial space, another geodesic orbit submanifolds with some special subgroups. For example, nilpotent group, solvable group, and semi-simple group. Okay, in some sense, This result says that general geodesic orbit Riemannian space is constructed from more simple bricks, a little of nilpotency, a little of semi-simplicity, and so on, so on, so on. But not so easy, really, not so easy. And some another results. It's a result from my recent paper. The inner product, now we discuss inner product that generate a geodesic orbit Riemannian space, should not be only H invariant, but also invariant with respect to normalizer of unit component of H. What does it mean? This means that if we have geodesic orbit space, then it should have more symmetries as usual homogeneous space. It should be. Okay. And some unexpected relation between various classes of Riemannian spaces. For example, some relation between Killing vector field of constant length in geodesic orbit spaces. It's not so not so easy to understand, but we have these results. If G mod H G is a geodesic orbit Riemannian space, G is Lie algebra of Killing fields, which we identified with Lie algebra of group G, and A is an abelian ideal of G, then every vector field from A has constant length on this geodesic orbit Riemannian space. That's also a little strange, but it's easy to check, really easy to prove. And we have observation that interrelation between various geometric objects are sometimes very unexpected. Very unexpected. Okay. Now we consider a little more serious structure result. We consider arbitrary geodesic orbit Riemannian space, G mod H rho, for example, rho, and H invariant decomposition, and consider M. It is a reductive complement to H with respect to Killing form. It's easy to check that this definition is correct for any homogeneous space. B is a Killing form and rho generated by inner product on M. Then we consider, let's consider operator A related with the Killing form by this formula. In some sense, it's Killing operator, yes, this Killing form and this some operator. And this operator is symmetric, and we have decomposition of M into the eigenvalue, eigenspaces of this operator with respect to various eigenvalues of this operator. It's a very usual thing. And now we have some results that's quite technical, but in any case, this result shows that a restriction, the property to be geodesic orbits is very, very restrictive, in fact. For example, if we have two vectors from different eigenspaces of operator operator A, and then there are some vector in centralized Z1 from centralizer of vector X and H, and Z2 from centralizer of vector Y and H in H, such that we have this quality. These brackets could be decomposed as this sum. It's quite strange. In particular, if centralizer is 0, then we have that this bracket is in another eigenspace. Okay, is centralizer for some eigenspaces 0, then we have this bracket in another eigenspaces. Consequently, if both centralizer are 0, we have that this bracket is simply 0. It's very, very restrictive, in fact. This theorem provides new tools in the study. Yes, sorry for typos. In the study of geodesic orbit Riemannian manifolds. These tools related to principal orbit types for linear action of compact Lie groups, because we deal with compact Lie group H, which is isotropic group, and we consider the action on the eigenspace, or in other words, on the model P. Hence, we can apply very serious theory of this representation theory to get some result in our cases. Yes, for example, this one, I don't explain all these formulas. You should believe that this restriction, this property is very restricted, because we have many technical, simple technical small results that are very restrictive in general. Hence, if you consider all this small restriction together, it's quite possible to get some partial classification of geo spaces. Some partial classification is possible to get. And the most serious result may be this one. It is a classification of all simply connected. It's not so serious restriction, because we can consider geo spaces up to local isometry. Simply connected geodesic orbit Riemannian spaces with positive Euler characteristics. I recall that homogeneous spaces, compact homogeneous spaces, could be either positive Euler characteristic or zero Euler characteristic. And positive Euler characteristics means that the ranks of G and H of isotropic group and isometry group are the same. In fact, it's equivalence property, which means that the homogeneous space G mod H has positive Euler characteristic. Yes, in the paper by Alexeyevsky, Arventa, Yurdos, they classified all non-normal invariant geodesic orbit metrics on flag manifolds. What is a flag manifolds? We take a group G and some torus in this group, and H is a centralizer of this torus. If H is centralizer of this torus, isotropic group is centralizer of some torus of isometry group, this space called flag manifold. This problem for classify geodesic orbit metric on such manifolds reduced to the case when compact group is simple, and they prove that there exist only two series of flag manifolds of simple groups which admit such metrics, non-normal geodesic orbit metrics, namely weakly symmetric spaces. This one, this series depend on value of natural number n, and the second family, similar to the first one, also dependent on the value of n. Equipped with any non-normal invariance matrix dependent on two real parameters. It's some technical, but in any case, if we have geodesic orbits manifold, geodesic orbits space of positive Euler characteristics, and the metric is not trivial, non-normal, isn't generated by invariant metric on the isometry group, then we have only two families of such spaces, which some special metrics on these spaces. It's very strange, very unusual, because there are too few examples of such manifolds, in fact. Therefore, one can think that the general problem classification is very easy, should be very easy, but it's not the case, because this case of positive Euler characteristic is very, very special, very, very special, in fact. Okay, now I should recall that these families have one and the same first element. When we consider n is equal to, then we have one and the same six-dimensional space. And in fact, it could be considered construction of such metric in details, but I want to omit some details in our discussion, because if you want, you can find these details in the presentation. It's not so difficult. This is a structure of general geodesic orbit metrics on any of these spaces which we discussed earlier. Therefore, we have two-parameter metrics. We take a normal matrix, which denoted by these symbols, and change it, multiply by some positive numbers x1 and x2 in different directions. Okay, it's not so difficult to check, in fact, that these metrics have property to be geodesic orbit. But it's very difficult to prove that only this example we can get in these cases. Okay. This more detailed description of such spaces. And in our paper with Professor Alexeevsky, we generalize these results from flag manifolds, from all flag manifolds, to all homogeneous spaces of positive Euler characteristics. It's, in fact, this class is more extended, more seriously extended than simply flag manifolds. But in any case, examples are the same. If we consider all geodesic orbit space with positive Euler characteristics, then metrics should be either normal, or we have the same exceptional two families of spaces as in flag manifold cases. Hence, we have complete classification in the case when homogeneous spaces is of positive Euler characteristics. And in fact, we should consider some idea how to prove. I explained it's only main idea. The main idea is the following. If we have some big space with this property, then we can consider some small subspace more seriously to say, geodesics, totally geodesic submanifolds, small dimension. It's possible to find by some tricks, by some special results. It's possible to find totally geodesic submanifolds in any given geodesic orbit space, such that these totally geodesic submanifolds, it's also homogeneous. It has also positive Euler characteristics, and the group G is very simple. It has rank 2. It has, therefore, the homogeneous subspaces, which is this totally geodesic submanifolds, it's has small dimension. And in fact, we can write down all such examples and check it by hand. This idea allows to get complete classification, but it works only, I repeat, the case when we have spaces of positive Euler characteristic. Okay, and the main technical result in this case is this proposition: every closed totally geodesic submanifold of G or Riemannian manifold is itself geodesic orbit. And there is some similar result for generalized novel homogeneous space, which we will discuss a little later. I try to explain what does it mean. If we consider naturally reductive metric, then construction is pure algebraic. We have some inner product on Lie algebra, some decomposition, and so on, and so on, and so on. Pure algebraic construction. And therefore, many geometer wants to get some inner characterization, some geometric characterization of such spaces, because naturally reductive spaces are very interesting. They have very interesting properties, have many applications, and so on, so on, so on. But what is a geometric characterization? It's not so easy, because, for example, if you take totally geodesic submanifolds of naturally reductive space, it should not be naturally reductive itself. Hence, not so geometric property. But if we consider more general class geodesic orbit spaces, then it's, in some sense, it's closure, some type of closure of naturally reductive spaces in some idealistic geometric sense. We take closure of algebraic construction, naturally reductive spaces, and get geodesic orbit spaces. And this is very good geometric class, because, for example, every totally geodesic submanifolds of such manifold is also geodesic orbit. It's very good geometric property. Therefore, we have good closure from geometric point of view. Hope I explained a little why this class is important for geometry. Okay. Now, how to find this totally geodesic submanifold? We have good results, good technical result by Alexeyevsky. Let G mod H G be compact homogeneous Riemannian space of manifold, and T any torus in H in isotropy subgroup. Then centralizer, connected centralizer of this torus is such that its orbit through the initial point is necessarily totally geodesic submanifold of a given manifold. It's very good, very simple, very nice construction. I recall that the simplest torus is circle, and in any compact group we can find at least one circle, non-empty, of course. Therefore, we have some torus in H. We can consider centralizer of this torus. We can consider orbit of this centralizer. We will have some smaller manifolds, some totally geodesic submanifolds. And if we try to get it better, we should find a good torus for this aim, for this goal, in order to get the totally geodesic submanifolds of low dimension. It's easy. It's easy technically, but not so short. But main idea is this one. Okay. Now we discuss some other recent results on geodesic orbit Riemannian spaces. Another natural problem: classify such spaces in the case then that the isotropy representation has exactly two irreducible components. Because if we have one component, it's easier geodesic orbit space, it's normal homogeneous space. But if we have, say, two irreducible components, we have many examples of such spaces, of course, and compact and non-compact and so on. And it's reasonable to start investigation, to start study from these partial cases. And this case not so easy in general, but in the case of compact and simply connected spaces, we have complete classification. And this paper is solved in our paper with Jackie Chen. And I'll skip some technical proposition. This some classification of type of such spaces. And the most interesting is the 7th one, when G, the algebra of G, is simple compact Lie algebra. All other are very special. And in the case when G is compact and simple, then we have also classification which is not so hopeful, only 9 spaces, only 9, not spaces, but families of spaces, because we have 1 and 2 parametric families somewhere. Okay. The proof is quite complicated because we should use both classification of all homogeneous spaces with 2 reducible components and some results or characterization of geodesic orbit spaces and so on, so on, so on. It's very complicated result by proof. But statement not so awful, really, in fact. Now we have that, we see that all these spaces such that metric G-invariant matrix has the space of G-invariant metric has dimension 2, and only in this case we have 3-dimensional space of G-invariant Riemannian matrix. Okay, it's some technical details. Now, some ingredients of the proof. I thought that I said that we use some classification results the classification of simply connected compact homogeneous space with two components in the isotropy representation by Dickinson and Kerr. Some important ingredients, another important ingredients was classification of geodesic orbit spaces fibered over reducible symmetric spaces by Hiroshi Tamaru, and so on, so on. Technically, not so easy, really. Now, we will discuss some results about geodesic orbit space, which are diffeomorphic to Euclidean space. Yes, I recall that if U is connected semi-simple Lie group of non-compact type and chi subgroup such that the corresponding Lie algebra is maximal compactly embedded subalgebra, then U admit an Iwasawa decomposition. U is product KS, where S is simply connected solvable Lie group, and the intersection is trivial. And we will say that solvable Lie group is Iwasawa group if it is a solvable Iwasawa factor of some semi-simple Lie group. It's just definition. What is the Iwasawa group? It's some solvable Iwasawa factor. Okay. Okay. Now we have results about geospaces diffeomorphic to Euclidean by Gordon, Karen Gordon, and myself. Let M be n-dimensional simply connected geodesic orbit manifold, then the following are equivalents. M is a Riemannian solved manifold. It's admit a simply transitive solvable group of isometries. M is diffeomorphic to Rn. And in the above notation, there exists an Iwasawa group S, a simply connected important Lie group N, and the left invariant metric H on the product SM, so that the corresponding Lie group with this metric is isometric to a given space. Moreover, N is at most two-step nilpotent. Is more or less good description of such geospaces, because in fact we can consider all this all details in the construction and so on and so on and so on. Therefore, we can say that this case also is done. All geospaces diffeomorphic to Rn, Euclidean spaces. Okay. Yes, and another result from the same paper assumes that Mg is geodesic orbit manifold diffeomorphic to Euclidean space. Then Mg is isometric to one of the following. The first type, Riemannian symmetric space of non-compact type. The second, and simply connected Riemannian geodesic orbit nil manifold of step size at most 2, and the total space of Riemannian submeasurement with totally geodesic blah 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 is a combination of first and second. Okay, we have both properties and some structure results which could be useful in some another study. Okay, another results, we have complete classification of geodesic orbits metric on this on so-called Leggero-Bata spaces. I recall what is this. M is connected compact simple Lie group, and we can consider the homogeneous space f to the power m mod diagonally embedded f. Here, this is another variant of definition by formulas. And such homogeneous space is called Leggero-Bata space. And what is the problem with these spaces? They are It's very special spaces in the following sense. If M is 2, we have simply a reducible compact symmetric space of the second type. Okay, but if we take M3 or more, then we have more complicated structure. The most important property is the following. If we decompose complement to the isotropy subgroup into irreducible subspaces, then all these subspaces are isomorphic each to other. It's very, very complicated because all these subspaces are almost Lie algebra F, almost in some sense. It's easy to check it for M is equal 3, but if we have 4 and more, then it's not so easy to check all variants. For example, if we have, if you want to consider all invariant metrics, then the dimension of the space of all invariant metrics is M times M minus 1 divided by 2. It's very serious. And some components could be considered, could rotate around another one, and so on and so on and so on. It's very complicated spaces from the point of isotropy representation. Very complicated. And almost it's not so easy to find papers where authors works with all metrics. They choose only some subfamilies, which is more or less simple, and so on. But we want to consider all metrics, and it was not so easy really. It is some technical problem, very serious. In any case, we have a classification. And the most interesting result is the following. A Legere-Bata space with invariant remaining metric is geodesic orbit space if and only if it is naturally reductive. Therefore, in these special subclasses, Legere-Bata spaces, it's the same geodesic orbit matrix and naturally reductive matrix. It's very strange, but we have such examples. For example, this. And of course, it's interesting to find all such homogeneous space with this property, but it's very, very difficult. I don't know, even reasonable conjecture what is the true result. Okay, in any case, it's possible when the space of naturally reductive matrix and the space of geodesic orbit are the same. Okay. And there are some other results. I don't explain details of this result. For example, classification of geodesic orbit matrix on all spheres. On geodesics orbit on some nil manifolds shaded with some type of graphs by Nikonorov3. In our recent paper with Nikonorov3 and Chen, we classified all geodesic orbits Riemannian matrix on all compact simply connected homogeneous space G mod H, where the isotropy group is simple. It's quite serious part of general homogeneous spaces. The restriction only on subgroup isotropy. It should be simple. All such spaces are studied, and we know all geodesic orbit spaces on such, all geodesic metric on such spaces. And there are some results by Suris, some Chen, Chen and Zhu and Arvanita Yorgos. Dushik has some service about some another result. You can find it in the reference if it's interesting. Now, a little about another idea, another metric idea by Professor Berestowski. What is delta homogeneous Riemannian manifolds and why it's interesting? Okay, I'll try to explain from the definition. Let's consider any metric space M with matrix M row M. It's calls generalized normal homogeneous, or another term delta homogeneous. It's equivalent. If for any 2 points x and y from M, there exists self-isometry F of this space, which moves x to y and which has the maximal displacement exactly at the point x. This means that f of x is y, and matrix between x and f at x is greater or equal matrix between z, f at z for all points z. Therefore, we have maximal displacement on x. Okay. If we consider, say, two-dimensional sphere and take any point, Euclidean sphere, round sphere, take any point x and y and consider this in equator and round this sphere about around axis, then we can move point x to point y with the maximal displacement. It's easy to see. Yes, you can easy to check it. If we rotate the sphere around some x, then the maximum displacement we have exactly on equator. Exactly on equator. And therefore, for any point x and y, we can find such isometry. Therefore, we have this situation, and this sphere, two-dimensional sphere, is generalized normal homogeneous by definition. Of course, the same we can say about another round sphere in another dimension, and for many other good spaces. And if we change a little definition and of generalized normal homogeneity and change inequality of this inequality to the equality, then we get a definition Clifford-Wolff homogeneous. Clifford-Wolff homogeneous metric space. What does it mean? It's almost the same, but we have Clifford-Wolff translation. It is an isometry which move x, y, and which moves every point the same distance. The same distance. It's not so easy to consider in compact case, but Euclidean plane, very good example, because we have translation, parallel translation. It's of course what we need. It's Clifford-Wolff translation. Therefore, Euclidean space is Clifford-Wolff homogeneous. But we also can say that round odd dimensional sphere are also Clifford-Wolff homogeneous. It's not so easy, but it's very well known from results of Clifford himself. Okay. If we have Riemannian manifolds, we can use the same definition, same definitions, Clifford-Wolff homogeneous and generalized normal homogeneous, with respect to inner metrics which generate by Riemannian tensor, of course. Hence, we have class of Clifford-Wall homogeneous Riemannian manifold, say Euclidean spaces, yes, and class of generalized normal homogeneous spaces. Okay. And what is characterization? It's quite strange, but one of the characterization is the following. A compact Riemannian manifold G mod H G is J generalized normal homogeneous if and only if there exists a G invariant centrally symmetric relative to zero convex body B in Lie algebra G such that the orthogonal projection of this body to P is exactly the ball of radius 1. The ball of radius 1. It's strange a little that we consider convex body if we consider ellipsoids, then we have definition of normal homogeneous. But we consider more general figures, more general bodies, any arch invariant centrally symmetric convex body. From the first sight, one can think that it's nonsense, because it's very strange that some strange convex body which is not ellipsoid gives a projection ellipsoid in P, but it's interesting. But it's interesting that this is the case. For example, if we take any known example of generalized normal homogeneous spaces, which is not normal homogeneous, we have find some body which is not ellipsoid with this property. It's very strange, but in fact, some relation between Finsler and Riemannian geometry of very strange kind. We have some Finsler structure on the isometry group, and after projection we have Riemannian structure in the homogeneous space. But it's true, we have such situation. And moreover, we have classification of such spaces with this property in case of the same positive Euler characteristic, because in this case we have more serious technical tools for classification. And of course, I should note that all generalized normal homogeneous metrics automatically is geodesic orbit, because from this property to have delta shift, to have spatial isometries between x and y, it's easy to prove that there is any geodesics is orbit of some one parameter isometry groups, really. Hence, we have some strange class. It's more than normal homogeneous, and it's a part of geodesic orbit. It's a part of geodesic orbit, and inclusions are strict from both sides. From both sides are strict. We have classification in positive Euler characteristics. You see the same families and in theorem about classification of geospaces, because we know it's partial case of geodesic orbit, but the most serious restriction by parameters of metrics. In any case, we have classification, complete classification, and in the case of positive Euler characteristic, we have all done in this case. Yes, all done. and some corollaries. I'll skip it because it's very, very strange corollaries from geometric point of view. But I also should explain that there are some techniques, some tools, which was how to say, these tools were obtained in our papers with Professor Berestowski. We find the methods how to generate new generalized normal homogeneous metric from a two given matrix, for example. We for this methods we need the notion of two means bar theory in convex geometry and so on, so on, so on. I won't skip the details, but I recall that there are some methods which allows to construct new metrics with these properties. Okay. And also I skip this, some technical results. And these ideas allow us to classify all generalized normal homogeneous metric on spheres. We know that there are several Lie groups that act transitively on spheres. Therefore, it's interesting to consider various these groups and classified properties of corresponding invariant metrics. And in our paper with Professor Berestowski, we classified all generalized normal homogeneous metrics on spheres and all Clifford-Wall homogeneous metrics with respect to all possible connected isometry transitive groups on given sphere. It's very technical, very interesting in some partial cases because we use some ideas from quaternions and so on and so on and so on. Very interesting paper, in fact, by using various tools together. Okay. Now, yes, a little. Note also that every of the above results gives an example of Killing vector field of constant lengths in the algebra corresponding to the group G. It's very strange, but it's fact. We can consider, we can generate such example, Killing field of constant lengths on the sphere, on a given sphere. And let's consider homogeneous space G mod H with compact subgroup H. And formally, we are interested in the following question: what kind of invariant Riemannian matrix does this space admit? For instance, we may focus on some natural characterization on invariant matrix and so on, and so on, and so on. This is a topic of our next lecture. Next lecture will be in a week. We will discuss the Ricci curvature, Ricci operator, the eigenspaces, the signature of Ricci operator, and so on, so on, so on. But now I want to stop on these results. Okay.